How's it going? How are you? Good. How's your day going? Good. You guys doing well? Good.
If I have to go through all the content that you have covered so far, if I have to do it efficiently, what all things should I be covering step by step? Should I be first reading the reference or going through the lectures again?
Yeah, I would read the book. The book is the best, right? If you read the book, then you'll be able to, what's going on here? If you read the book, which is part of your homework each week,
Yes.
then you'll really understand the concepts. Then you can go back to the lecture notes and they will really make a lot more sense, right? That's what I would recommend. Oh my gosh, where's everybody? How's your research going? Good? Yeah, sinusoidal, right? That's good. Oh, yeah, yeah. The beginning of any new problem you solve is a lot of literature, right? Yeah, for sure. Who? Say it one more time. No.
He actually, he is awesome.
Really?
Even he passed away, but he was a professor here. I didn't know that.
Oh, wow.
Yeah, I have words nonlinear oscillation. When you read it, it's like reading a novel.
Oh, wow. Very nice.
Yeah.
I didn't know that. Okay, let's go ahead and get started, guys. Just to remind you, we'll be bringing up this reminder each day, each lecture that we have. Today is lecture 11, which is September 28th. And after that, we're going to launch into the month of October. And in October, there are a lot of things happening that you need to be aware of. So the first thing is you're going to have a new homework today. It's up on Canvas already. So that is due a week from today, which is the 5th. So make sure you have your homework done in a week from today. And there's a midterm on the 17th. It's an in-class midterm. So you'll have an hour, 15 minutes to complete a problem or two, similar to the homework. So it's going to be a homework style problem. You'll be able to use your notes. So if you need them, I'm wondering if I should allow you to have electronic devices. Probably not, but I don't want you to have to print everything. Okay, so at this point, print your notes. Put them in like 4 slides per page, so you don't use up a bunch of paper. But print your notes. For now, it's going to be no electronic devices, but it's going to be in-class exam, and you're just going to have to do homework style derivations. All right, you'll have an hour and 15 minutes. So be prepared for that. If you're doing well in the homework and you're following those derivations, it'll be very similar. All right. Okay, after that, we have lecture 17, which is on October 24th. And remember, it starts at 8 a.m. instead of 9:30, and it ends at 9:15. And it's not in this room, it's in Torque 1030, which is across the hall. And the reason for that is I have a National Science Foundation NSF review panel that I'm required to be at. Okay? So of course, if you can't make it at that time, you can watch a recording, but it will be recorded as well. But it'll be in that room at that time on that day. All right, good. Any questions on the schedule and things that are coming up? Yes?
Can we use the reference book in the midterm exam?
Yeah, definitely. You can bring your book. And you can bring your book and print out any of your notes. And if you want, you can bring your graded homeworks. But I don't know if that'll help you. Whatever you want, as long as it's not an electronic device. And technically, I don't even think electronic device would be a problem, but at this point, it's going to be no electronics. All right? Great. Okay. All right. Let's get into the lecture. Okay. All right, so what are we doing? Last time we solved the wave equation in cylindrical coordinates. Now we're going to solve it in spherical coordinates. All right, spherical coordinates is one of the most often or popular used coordinate systems because whenever we solve radiation problems due to current sources, if we're far away from the current source, which is called the far field, then no matter how big the antenna is, it looks like a point, right? So it radiates in a spherical way. Okay, so in spherical coordinates, the electric field can be expressed in the following way. We have a vector function of 3 variables, r, theta, and phi. It has 3 components, er, e theta, and e phi, in the r hat, theta hat, and phi hat direction. And each of these scalar components are functions of these 3 variables, right? 2 angles and a length. And if you evaluate this scalar function, then you pick up the r component, evaluate this scalar function, which may be different than this one, and you get the theta component. Evaluate this function, you get the phi component. You piece these 3 unit vectors scaled by those function values, and you construct the vector E, right? At all locations. So let's substitute that electric field into the vector wave equation. We know in this coordinate system that the Laplacian isn't distributable, so we have to use the alternate form, which is the gradient of the divergence of E minus the curl of E, and that is equal to minus beta squared E by nature of the wave equation. So after lengthy manipulations, it results in 3 scalar PDEs, right? So remember what happened in rectangular coordinates? We did the same thing. We got 3 scalar PDEs that were all of the identical form, right? So we could solve any of them for EX, for EY, or EZ, and we could obtain the solution for all components analogously. Here, or in cylindrical coordinates, we ended up with 2 coupled equations and 1 uncoupled. We solved the uncoupled equation with the restriction that a solution or any electric field that we're trying to describe in cylindrical coordinates has to be described in terms of the z component. If we're solving the wave equation, it has to be a z component, but that doesn't restrict us much because we can have a z-directed electric vector potential, magnetic vector potential, electric and magnetic fields, and those 4 combinations, you can create a lot of different fields. In this case, we're going to have 3 scalar PDEs, which are all coupled. Each of these scalar PDEs contain ER, E theta, and E phi. So solving them is hopeless, right? So what we're going to do is we're going to use an alternate approach. The alternate approach is going to involve potentials. So we're going to go through potential theory next, yeah? Any questions? All right, very good. Whoops. Okay. So let's introduce auxiliary potential theory, all right? Although we will study auxiliary vector potentials more later in the course, we will introduce them here for the purposes of understanding how the wave equation is constructed in spherical coordinates. The vector potentials are typically used to solve the inhomogeneous wave equation. That's what we're going to use them to solve later in the course. That's where we're going to really dig deep into this. When we solve the inhomogeneous wave equation, what is the radiation due to source distributions of current? So the right-hand side would not be equal to 0, but however, here we will use them to derive a homogeneous wave equation for TE to R and TM to R waves in spherical coordinates. So what does that mean? I get two sets of solutions from solving the wave equation under this apparatus. I get, here's the R vector. So, you know, my arm is, the elbow's at the origin. The R unit vector is that way. I can construct mode solutions that are transverse electric to R. So the electric field is transverse to the direction R, and a different set of modes that are transverse magnetic to R. And I can add up these two modes to construct a third set of solutions, which are weighted superpositions of TE to R and TM to R solutions. Then I can construct a lot of different solutions. Okay. So that's what we're going to do. So here's a little plot or a little diagram taken from your book, which kind of illustrates what we're trying to do here. We have sources, J and M, right? That's what we're given whenever we want to solve an electromagnetics problem. We have sources J, electric current density, and M, magnetic current density. You can either integrate these directly to get the radiated E and H fields. That's what it means to solve an electromagnetics problem, is to obtain E and H everywhere, right? Maxwell's equations are differential equations, which have functions as solutions, and they're differential equations in terms of E and H, right? So if you solve that differential equation pair that are coupled, then you get E and H. Those are the solutions to Maxwell's equations. So given the sources, we can get the E and H directly in one path, right? This is a difficult path to take, and we'll see why. Probably later in the course, we'll dig into this deeper, but going this path is very difficult. It is easier to go in this auxiliary path where we have a two-step process where we take the sources J and M and we calculate what's called a vector potential, all right? A is associated with J, and F is the electric vector potential associated with M, all right? And then there's these other potentials, but don't worry about those for now. To get to A and F from J and M, it's an integration process. And then to get to E and H, once you have the potentials, it's a differentiation. It's kind of like gravitational potential energy and the gravitational force field, right? You have, there's a force field of gravity, and at each point within that force field, you can define a potential, gravitational potential energy, which is related to the height above the center of the earth and so forth. So with every force field, there is a potential associated with it, right? So here we're going to define potentials in terms of their vector potentials. So they have direction. They are the electric vector potential, the magnetic vector potential. All right. Okay. Good. So let's see how to construct these. For now, let's construct a mathematical vector field A. We're going to introduce a new vector field A. It doesn't have any physical origin at this point. It's a mathematical tool that we're going to use to allow us to easily solve problems involving sources. And in this case, to derive a wave equation, which is homogeneous, meaning that it doesn't involve sources, but it allows us to construct modes and solve the wave equation in spherical coordinates. All right. So let's introduce this mathematical vector field A, and we just have to ensure that if we do bring into existence, bring forth this new mathematical vector field A, that it satisfies all of Maxwell's equations. So as long as we check all those boxes, then our new mathematical vector field A will be a valid approach. So we're going to define H as 1 over mu curl of A. That's a differentiation, right? The curl operation, remember upside down triangles, nothing but partial by partial X or Y or Z, combinations of spatial derivatives. So we're going to say that H here is related to A through a differentiation as the following. H is equal to 1 by mu curl of A. All right? Good. That's a definition. We're going to say that that's our starting point. We just have to make sure that this chosen definition, see, remember, in the beginning of the course, lecture 1, we talked about vector Helmholtz decomposition theorem, right? What are the two properties of a vector field we need to define in order for it to be uniquely specified? You remember? Curl and divergence, very good. So we've specified the curl of A now, right? So we're halfway there. So we're going to make this conjecture that H, we're going to specify the curl of A to be equal to H, all right? Now we just have to make sure that this definition satisfies Maxwell's equations. So that's what we're going to do. Let's check them one by one. The reason why we chose this form first off, because the divergence of B must equal to 0, Maxwell's equation. So let's plug in what we have for B. It's curl of A, right? Because mu times H is B. So we have the divergence of the curl of A, that's equal to 0. So this choice of a representation of B satisfies this Maxwell equation because the divergence of the curl of any vector field is equal to 0 by identity, by definition, right? Or by identity. Great. Let's check Faraday's law. So the curl of E is minus j omega mu H. We have a definition for H, a new definition in terms of its potentials. So minus j omega mu minus j omega curl of A, right? Now, since this is a curl operation and this is a curl operation, and the curl is a linear operator, it means it can be distributed. We move this term to the other side and we factor out the curl operator. So we end up with the curl of E plus j omega A equals 0, right? Good. Or we know that the curl of any vector field, if it is equal to 0, then that vector field can be represented by the gradient of some scalar potential, right? That's another vector identity. So that means because any curl is vector field is also the gradient of some scalar field, right? This is a conservative vector field. Then we can say that E plus j omega A is minus the gradient of phi. It's a common operation. So minus phi, we can solve for E. E has to equal to minus the gradient of phi minus j omega A. Does this look familiar? If I remove this part, does it look familiar? That's statics, right? E equals minus gradient of V or phi, right? Now I can specialize this solution to statics by saying in the statics, omega is equal to 0, right? Because F is equal to 0, it's DC. So if I made omega goes to 0, DC, then I recover the DC result. And we know the electric scalar potential is related to the electric field through the minus gradient operation, right? This new form also applies to dynamics. So be cognizant if you're solving problems involving time varying or non-DC, non-statics, time varying, right? Maxwell's equations, that you cannot use E equals to minus gradient of phi. Right? That's a statics result. You need this result. This applies to dynamics. So we have another result. E equals to negative gradient of phi minus j omega A. So these are force fields now in terms of the derivatives of their potentials, right? We have H in terms of a potential, a derivative of it, right? And we have E in terms of its potentials. Phi is a potential, electric scalar potential, and A is the magnetic vector potential. So E is expressed in terms of its potentials. To differentiation, right? What derivative is this? Time derivative, right? In time harmonics, partial by partial T becomes j omega, right? So this is a temporal derivative, a spatial derivative of a scalar potential, a temporal derivative of a vector potential. That gives you your electric field. So it's differentiation path, yeah? All right. Now let's check Ampere's law. Ampere's law is the curl of H equal to j omega epsilon E plus J. We have the curl of H we know is 1 over mu times the curl of A. That's equal to j omega epsilon. And we know what E is, right? E we found on the last slide is, so remember, this here is H, and this here is E in terms of their potentials that we got on the last slide, plus J. All right, well, if we factor out that mu and multiply through, assuming mu does not depend on position, we end up with the curl of A minus omega squared mu epsilon A is equal to minus j omega mu epsilon gradient of phi plus mu J. All right, good. Okay, so this is almost a wave equation, right? But that's another equation that comes out of Maxwell's equation with our assumed potential for H. Next thing we'll test is the electric Gauss law. The divergence of D is equal to rho. So the divergence of epsilon E is equal to rho. And we know what E is in terms of its potentials, equal to rho. Then we can derive the following expression, which reduces to del squared phi plus j omega divergence of A is equal to negative rho over epsilon. All right. So another wave equation, right? Okay, They're almost wave equations. They're not because they have this extra term in here, right? If we could get rid of, so remember, this has some divergence in it, right? Divergence of A. And we have the divergence of A here, right? So remember from the Helmholtz decomposition theorem from lecture 1, that a vector field is uniquely defined when both its divergence and its curl are defined. We have already specified what the curl of A is. We are free to choose what the divergence of A is, right? It's still a mathematical vector field that we're constructing. So we're free to choose what the divergence is. Once we have fixed the curl and the divergence, then A is uniquely defined. So we're going to choose the divergence of A equal to minus j omega mu epsilon phi. And the reason why we're going to do this is it's going to simplify these two equations here that I've underlined at the top of the slide into something much more familiar and solvable. This choice of the divergence has a particular name. It's called the Lorentz gauge. All right. Okay, so if you do that, here are the 4 equations that we derive from Maxwell's equations. If you apply the Lorentz gauge to them, then you end up with H is equal to 1 over mu curl of A. E is equal to minus J gradient to the divergence over omega mu epsilon, right? Because E was gradient to phi, but we have a definition for phi now, which is phi is equal to minus 1 over j omega mu epsilon times the divergence of A. Plug that into here, we get E completely in terms of A. E completely in terms of A, H in terms of A, and then to the wave equation up there, if we apply our identity to the curl of A, we can then identify what the divergence of A should be. And we end up with the following expression. The Laplacian of A plus omega squared mu epsilon of A is equal to minus mu J. This we're going to solve later in the course. This is much easier to solve than other forms involving E or H. Del squared E plus K squared beta squared E, right? This is beta. Omega squared mu epsilon is beta. It's equal to some form of J on the right-hand side. This is easier to solve. We'll solve that later when we're given a source distribution. And then there's a wave equation for the scalar potential, but you don't need to solve that one, right? Remember, these two are related by the continuity. Divergence of J is equal to minus j omega rho, right? You don't need to solve this one. You can solve this one alone. And once you obtain A, which is a solution to this differential equation, you can plug it into here, here, and here, and you get E and H. All right? But we'll do that later in the course. Okay. Any questions? All right, so let's derive a wave equation for spherical coordinates using the result. We now return to our problem. We derived the expression, the curl of A minus omega squared mu epsilon A is minus j omega mu epsilon gradient to phi plus mu J, right? That was what we derived on the previous slide before we applied the Lorentz gauge, all right? In source-free media, we can rewrite this in terms of, this term goes to 0 then, right? In source-free media. All right. Now, we have the curl of A minus omega squared mu epsilon A equal to minus j omega mu epsilon gradient to phi. We can do everything all over again. We start with the expression for E in terms of its electric vector potential. So we define E in terms of an electric vector potential, 1 over epsilon curl of F. It's almost the dual of the previous equation, except we pick up a minus sign. So be cognizant about that. You can repeat the entire process and you end up with the following. Curl of F minus omega squared mu epsilon F is, we have the gradient of some magnetic scalar potential due to magnetic sources and magnetic current density, right? Good. And you can derive the same equation for source-free media. So this is useful when we have magnetic sources present. If you have a magnetic source, then F and phi m become significant. And if you have electric sources, then A and phi become significant. All right? So how do we derive our modes using these equations? So to derive the TE to R modes, meaning that the electric field is transverse to the radial direction, TE to R, we may assume an electric vector potential in the R direction, right? So let's assume that we have F in the R direction, electric vector potential in the R direction, and set the magnetic vector potential to 0. So this is how you derive the TE to R modes. So we're going to call this E due to F, right? So the electric field, there's part of the electric field due to F and part of the electric field due to A. This component is E due to F. That's equal to minus 1 over epsilon curl of F by definition. That's equal to minus 1 over epsilon curl of R hat FR, because F only has an R component. All right? So this means that because E is related to the curl of R hat FR, that the electric field cannot have an R component. Whenever you take the curl of some vector, then you're trying to find the axis. So the curl of this vector, is the electric field, right? So the electric field is an axis of which F circulates about, right? So because of that relationship, if you have an R hat, if you have some component taking the curl of it, then this will always be orthogonal to that. We can see that here too, right? The curl of A, so the curl of A, yeah, here's exactly what I'm saying. The curl of A, you can also look at the definition of the curl of A in spherical coordinates. We have an R hat component, right? An FR. When we take the curl of R hat FR, then where is the R hat component is here? Here, we have an R component. And, oh yeah. Okay, so the vector that we're taking the curl of only has R component, right? Now look here, the R hat component is determined by phi and theta hat. So there is no phi hat or theta hat components. So there cannot be an R hat component, right? Mathematically, that's true. Physically, you're looking for an axis of which the vector field circulates about. So when you think of that, the curl of the vector field is orthogonal to the axis of rotation, right? There's an R hat here, so you can have a theta hat component. There's an R hat here, so you can have a phi hat component transverse to the vector field, right? So that's why it's TE to R, because the electric field cannot be in the R direction. So that's what the purpose of this construction is. TE to R, meaning the electric field is transverse to the R direction. If I set the electric vector potential to the R hat direction, take the curl of it, then this vector field E cannot have an R component. So it's a way to construct TE to R solutions. All right. So let's do it. Curl the curl of F. So we have our wave equation here. Let's plug in our F here. And let's build up this thing term by term, right? So we're going to solve this part first. So the curl of F here is the curl of R hat FR. Here is the expansion for only having R hat FR, right? We have a theta hat and a phi hat component, as we said on the last slide. Then we're going to take the curl of that result. So the curl of F. So here we have, so I've done that here for you, right? We have an R hat, theta hat, and a phi hat component, but it's all dependent on FR only, right? That's all we have to start with. Okay. Then we have the gradient of phi. Well, gradient is an easy operation too. So remember, these are the scale factors, right? Here's H1, which is 1. Here's H2, which is 1 over R. You guys did this in your homework. H3, which is 1 over R sine theta. Remember? Very good. Okay, the R, theta, and phi terms reduce to, so now we're going to separate. So here's R. So we have this part, R. We have minus beta squared still from here. And then we have minus j omega epsilon times the gradient of phi, but the R component of it is here. So that goes here, right? Okay. And then the theta hat component and the phi hat component. Okay, so now we have an R, a theta, and a phi component. They're differential equations, right? So, okay, so let's step back and understand what we're doing here, right? We're trying to find electric field modes that are in terms of this electric vector potential, right? And we're trying to construct TE to R modes. So what do we need to do? We need to solve for FR. If we can find what FR is, then we can obtain the electric field, right? So let's solve for FR. That's the whole point of this. We have three differential equations that are all in terms of FR. We need to find a way to obtain FR. So these two equations here, the last two, they can be satisfied simultaneously if we make this observation. Partial FR partial R is equal to minus j omega mu epsilon phi m. All right? And, or you can say that phi m is equal to minus 1 over j omega mu epsilon partial FR partial R. If you take this phi m and you plug it into here, then the equalities are satisfied in both cases for both components, okay? Good. So we now have a differential equation here we can solve, right? This one, and then we have this definition. Great. So the last two expressions, I'm repeating them here, or I'm repeating the result from the last slide here. We will substitute this expression into the remaining expressions, right? So we had, over here, we had, partial phi, partial R. We had phi here. So we had phi on the right-hand side of each of these. And we've now substituted them in to the right-hand side of each of these three differential equations, right? Oh, no, sorry. The first differential equation. My apologies. This one. So these two were already utilized in order to obtain this expression here. Now we're going to take that and plug it in to the third one, right? So if we do that and we, go through the algebra, then we obtain this final expression. Okay, these are just the steps that you go through to get to here, all right? Now this is a wave equation we can solve, right? So we can solve this wave equation. It's a homogeneous wave equation, and it's in spherical coordinates. We've derived it from a vector potential approach, but that vector potential approach, the construction of it satisfied all of Maxwell's equations. Therefore, this wave equation is constructed on the basis of satisfaction of Maxwell's equations, and is represented in spherical coordinates. The solution of this differential equation gives you FR. Once we have FR, we can take the curl of it and multiply by 1 over epsilon, and we can get E, right? That E that we get is a special set of modes or field solutions that are transverse electric to R. So we started with the wave equation in spherical coordinates, and we tried to plug in our expansion in terms of the vector components represented in spherical components into that wave equation. And we had three coupled scalar PDEs. All three of them were coupled together. We couldn't solve it. So then we turned to vector potential theory, and we derived a wave equation which satisfies Maxwell's equations for a vector potential component F, which is an auxiliary step. Once we solve this differential equation for F, we can then obtain E. And it all jives with Maxwell's equations. Okay, good. So now we just have to solve that, right? So I'll repeat it on the part of the slide. If we solve this homogeneous wave equation in spherical coordinates, we obtain F, right? And then from it, we can obtain E from the solution for F. This differential equation we can solve. It's a scalar PDE, right? For one component. And then we can obtain H from Maxwell's equations, which is in terms of the curl of E or the curl of F, right? Good. All right, great. Any questions? All right, then. All right. So let's do it. Okay, you can do the exact same thing for M2R, which means we're just going to solve the magnetic vector potential A, right? So you do the same thing. You assume F is 0 and A has an R hat component. That means we're going to get magnetic fields are transverse to R. And we derive this same exact wave equation, but it's in terms of AR. And then we can find E due to A now and H due to A by using A. We get H directly from A now, which is 1 over mu curl of A. In the previous case, we got E directly from F, but here we're getting H directly from A. And then we can get E from this result, right? So, okay, now we have both the wave equations. So in the end, they both look like this. They have this form, right? Del squared plus beta squared into psi is equal to 0. Psi is a scalar, right? There's no vector above here, but that's the case, right? It's a scalar PDE. And we have FR over R is psi for TE to R modes, or AR over R is psi for TM to R modes, right? So now let's solve this wave equation in spherical coordinates. You guys, if you haven't seen your homework yet, you're going to do this. Actually, I think you're only doing the theta differential equation, Legendre. I do it all in the notes anyway, so you can copy it from here, right? But make sure you understand when you, the purpose of writing all that out is so you can write it to yourself, right? This, your understanding of it in your own words. And when you do that, the process of doing that is where you'll find gaps in your knowledge, all right? So let's solve it. Okay, we can solve this differential equation using our friend separation of variables. So psi, r, theta, and phi is represented as f, g, and h, where f is a function of r, g is a function of theta, h is a function of phi. Why do I do this? Because assuming this separable form, hopefully the result is that I separate the PDE into ODEs because each of these functions depend only on a single variable. So I can convert the derivatives, which are partial derivatives, into straight P's, which are ordinary derivatives. So that's the approach. So f, g, and h, we plug in. Oh, what's going on here? Okay, f, g, and h, we plug in, right? So we have to write the Laplacian in terms of spherical coordinates, and we have psi here, right? So this is the Laplacian in spherical coordinates, and it's equal to minus beta squared psi. All right? Then we plug in f, g, and h. We get this line here, right? G and h can factor out. That's the whole point of having this separable solution, is G and h can factor out of these partials with respect to r, and then I just have partial f as a function of a single variable with respect to its variable, then these become ordinary derivatives. So G and H come out, F and H come out of this one, and F and G come out of this one. And that's all equal to minus FGH. You know the story by now. We divide through by FG and H, and we obtain, and then multiply also by R squared sine theta, we obtain this differential equation. All right? So what do we notice? The first term here has theta and R. So it's not, we can't set it equal to a separation constant yet. This one has theta. We could do it here, but we're going to start here, right? Here we have 1 over h, partial squared h. Okay, so these should be ordinary derivatives. I guess I made that here. Okay, partial squared h, partial. Yeah, I would change, this is incorrect, right? Sorry, the other ones are, these ones are all ordinary derivatives. This should also be an ordinary derivative. All right, make that change. Okay, so that is the only function in this string that's a function of, oh no, we couldn't start here because theta is also here, right? So we had to start here. Phi, there's no other term that's a function of phi. This all equals to some constants in the end. So we have, that's not a function of phi. So we have to, we can set this equal to a constant, right? Which is minus m squared. This is a differential equation you've solved 100 times now. It's a harmonic functions are the solutions. The only function you can differentiate twice, add it back to itself, and you get 0 is sine, cosine, or exponential. So we expect in the phi direction, azimuth, we should have exponential functions or sine and cosine, periodic functions, right? Okay, so take that and plug it back into the differential equation. Oh my goodness, why does it keep doing that? So here we have, there's our separation constant, and we divide it through by sine squared of theta. If you remember here, we had sine squared of theta over here. So this term becomes r, and then we divide through by sine squared of theta. Let me see, where's the beta r? Minus beta r. So there should be a beta squared r squared minus beta squared r squared sine theta, right? Oh, I think we moved that here. Sorry. Yeah. So divide through by sine squared, and then move the beta r to the other side. That's remaining, right? So then you get this differential equation here. What do we notice here? This term and this term are functions of theta only, right? This term is not a function of theta. So we can set all of that to a separation constant. So that means this all is equal to some separation constant. We're going to call that separation constant minus n into n plus 1. All right. So somebody did this and probably started at a single constant, but then they noticed it'd be much more convenient if we set it equal to this kind of constant because it allows us to construct more familiar results in the end. So that's the motivation behind this choice of constants. It's still a constant, right? But it's this choice. You'll see why it lends itself nicely later on. So n is usually an integer. This is closely related to the Legendre differential equation. This one you're going to solve in your homework. All right, derive it and solve it. So it's all here though. All right. So it's closely related to the Legendre differential equation. Substituting in this separation constant for all of this over here, we get this differential equation, and this is closely related to Bessel's differential equation, slightly different. All right. So starting with our wave equation that is in terms of potentials in spherical coordinates, we've derived an azimuthal differential equation, which is a harmonic differential equation, Legendre's differential equation in the polar coordinate theta, and a Bessel differential equation in R direction, right? So you guys will dig into these in your homework. Good. So, okay, I guess I put it here. Yeah, so it's here. So you guys try doing it without looking at this, right? When you do your homework, then you'll understand it more. But it's up to you. If you just want to get it done and you can copy it, right? It's all here. So here's the differential equation. How do you solve it? Well, let's multiply through by g and use the product rule on the first term. So multiply through by g. All right. So let's move this to the other side, and we multiply through by g. That means this one. What? D2g. Where does this come from? Oh yeah. Open this up with the product rule. All right. G. So this is F, this is G. You know the product rule, right? This is F. This function is G, and we have to differentiate that product, F times G. So G times F prime plus F times G prime. And if you multiply through and use the product rule, you get this differential equation, all right? Okay, now we're gonna substitute X is equal to cosine of theta, and you'll understand this substitution in your homework as well. But X equal to cosine theta, which implies that sine of theta is the square root of 1 minus x squared, right? By definition. Because sine of theta is 1 minus cosine squared, and then check the square root of that. Then we have dx d theta. We can differentiate our substitution here, and we get minus sine of theta. We relate it back to this result. We get minus the square root of 1 minus x squared, all right? Take all of this, substitute it into our differential equation, and we've transformed variables to, so here's the first term. There, in this differential equation, we have that, we have this. So here's that term, and that term in terms of our substitution. And, okay, so to solve this, you're gonna need to use this identity, which is called the chain rule for higher order derivatives, all right? So make sure when you do your homework that you go through, understand that, all right? So the point of the homework is for you to dig into this. If you copy it, then you didn't learn anything. If you go and like off on a tangent while you're doing your homework and look up multivariate derivatives and you learn about this, then you've learned something in writing out your homework, right? That's the point. Because when it comes time to do research, there's not going to be a slide for you to copy from. You're going to need to go to the resources, learn about that, and come back and apply it to your problem. So it's a good practice, all right? Okay, 1 minus x squared. So now we have this term for this. We have this for this. And we know what cosine of theta over sine of theta is because we have cosine of theta is x, sine of theta is this. So plug all that in. We get this differential equation here, all right? Okay. Now, looks like there's some combining of terms going on. I think we distribute this, right? Yeah, distribute that and combine it with this term. And at the end, you get this, all right? At the bottom, this is called the associated Legendre differential equation. We derived a differential equation in terms of theta because we're working spherical coordinates that have theta as a variable, right? You can also express that in terms of x by making a substitution, and you're going to do that in your homework. But in the end, you get this differential equation, which is one that mathematicians have solved, and it's called the associated Legendre differential equation. It's tabulated and all of its properties are provided in the appendix of your book, which you're going to read as part of your homework. All right? So we can solve associated Legendre differential equation. So here it is. So the associated Legendre differential equation is a generalized version of Legendre's differential equation when m is equal to 0. So if you set m equal to 0, then you get back to the Legendre differential equation. So what obtains the Legendre differential equation? We will solve this one first. So this is the ordinary Legendre differential equation. We're going to do the same thing, right? So we don't know, we don't expect that this differential equation has a solution that we can write in terms of classical functions that you can write down. We got to construct our own function that has the right slope everywhere. That slope and the relationship between all of those slopes that satisfy this differential equation. So G, we're going to express now in terms of just an ordinary power series. We don't need to use Frobenius method because there's no singular point here. So C of K, X to the K, right? So we can differentiate our assumed solution for our expansion. We get this. We can differentiate it twice. We get this. We can take all three of these, plug them back into the differential equation. You'll see this is much easier when you don't have to do Frobenius method. These summations already start at K equals 0. And now we just have to run off some terms to get all of these to the same power now, right? Let's see. X of K minus 2. This is X of K minus 1. So the K minus 2 term is here. If we divide through by 1 minus X squared, hold on a second. K minus 1. I think what we're doing is just bringing these terms in, right? If you bring these terms in, then you end up having the same, you end up having this differential, or sorry, this equation here at the bottom. I'm pretty sure that's what we're doing. I did this a while. Yeah, so let's just verify that, yeah? So here, this n into the n plus 1, that is here. It appears unaltered, right? So we didn't multiply through by anything because that term would have been affected. Here we have minus 2x into this. Here's the minus 2. X comes in, that increases this power. X multiplied by x to the k minus 1 is x to the 1 plus k minus 1 is x to the k. Yeah, that's what we're doing. Yeah. Just bring all that stuff inside and you end up with this. So we still have this problem. This is k minus 2, but this is x to the k, x to the k, x to the k. This is 0, this is 0, this is 0. So you just have to work on this term now. All right. So I've repeated it here. If we let s equal to k minus 2, then at k equals to 0, s is minus 2, right? And we can say that k is equal to s plus 2. So then at k equals to 0, s is minus 2. So we convert this to s. When k is 0, s is minus 2. And here instead of k, we're going to have s plus 2. So we get cs plus 2. Every k here becomes s plus 2. K here becomes s plus 2, but we subtract 1, we get s plus 1. Then we get x to the s. All right? Now, now we have all the same powers, right? Doesn't matter. This one's called K and this one's called S, right? It's the same thing. But we have this problem. So let's fix that. So S equal to minus 2 and S equal to minus 1 terms are 0. Oh, that's convenient, right? So if S is equal to minus 2, so let's run off terms for here. S equals to minus 2. Well, minus 2 plus 2 gives you 0 for that because the product. Minus 1 plus 1 is 0 for that. So we can rewrite this in terms of k equal to 0, x to the k. Now everything's good. We have the same starting index and we have the same powers. So we can factor out the summations and the function x to the k. And we end up with this. So we had the summation factored out and the x to the k factored out. It's all equal to 0. The only way, because x to the k is not 0, the only way for this to be 0 for all k is for this coefficient to equal to 0 for all k values, right? That's the whole point. So this has to equal to 0, the coefficients. All right, so we can solve then for ck plus 2, because we have ck here, right? And we have ck plus 2. We can solve for the highest order one, ck plus 2, and we have this difference relation in terms of ck. And then we have, what do we do here? K minus n. Okay, so, okay, yeah. So if you multiply this all out, k squared minus k, then you have a plus 2k, you can combine those two. And then you can you can combine it with this. You get this result, right? Oh, shoot, just algebra. All right, good. So here's G. We have found what the coefficients are. CK, CK plus 2 if we know CK, right? But we know okay, so let's start solving it, right? So if K is equal to 0, that's the first value in our expansion. We need all the coefficients in order to construct G, right? So we start with K equal to 0. C2 is, so K equal to 0 gets rid of all of these K's. You get minus, and you get n plus 1. You get 2 times 1, which is 2 factorial into C0. All right? Then you can do K1, K2, K3. And what we find is that everything depends on C0 or C1. So there's an even and an odd series. Good. So, all right. So if we take the even series, we're going to call that solution y1. The even series has x squared, x to the 4th, x to the 6th. It's only the even terms, all right? So we take the even terms from here. K equals to even numbers. Then we get, it's these ones. We get y1. The second solution is the odd series, which is C1, C3, and we have x cubed, x to the 5th, x to the 7th, all right? Okay, you're going to detail this in your homework. So we have these two solutions, y1 and y2. It is customary to choose the coefficients C0 and C1, those are the degrees of freedom, in the following manner. If you choose them in that way, then what happens is you end up with these functions. So there's even and an odd series, right? These are called the Legendre polynomial solutions, and they're plotted here. They go from, their domain is -1 to +1, right? I remember we made the substitution x equals to cosine of theta. So if x goes from 0 to, or -1 to 1, x equals to cosine of theta. If x goes from -1 to 1, then cosine of theta goes from, what theta gives you -1 for cosine? Pi, right? Pi. And what theta gives you +1 when you take cosine of it? 0. 0 to pi, right? Which is correct. If you have a spherical coordinate system, x, y, and z, the theta angle ranges from 0 to pi, right? All right, good. So these also apply. You can do a change of variables, go back, and this would be 0 to pi. And you get this expansion function as you change the angle theta. You can expand any function in terms of the theta variable. So on the surface of a sphere, a constant r, you can have some expansion in terms of that theta variable, and these polynomials is orthogonal, which is good because then you can set a series of them. If they're orthogonal polynomials, I could say any function g of theta can be represented as some a0 p0 plus a1 p1 plus a2 p2 plus a3 p3, and I can use the orthogonality of these polynomials to find those coefficients. All right, so they look like this. They're plotted here, yeah? Okay. Okay, so there's Legendre's differential equation. We have g of x, which is our solution, has some unknown coefficients, and pp of x and pp of minus x, all right? Where p is not an integer. And if p is an integer, then we have the same kind of thing with the Bessel function. If p is an integer, then we have to construct a third solution, which we call a Legendre function of the second kind, when p is an integer, and it's called q, all right? And we have p of n you can find through this formula. You can find all the polynomials. They're all listed here. Not all of them, but there's some, right? If you substitute x equal to cosine of theta, then you can get so q here is obtained in the same way as we obtained y when we saw Bessel's differential equations, cylindrical coordinates. I'm not sure why I said x equal to cosine of theta. Oh yeah, duh. These are all in terms of theta, right? So, these were in terms of x, but you can substitute back in for theta and you get these. And these are the polynomials for q, which is the second solution, second linear the independent solution whenever you have an integer n. So you'll see these a lot, Pn. Pn, you're gonna use that a lot in this course. Pn, and what we're gonna have is Pn and there's a superscript m, which we'll find later when we solve so this was the solution of Legendre's differential equation for m equals 0. But for us, for our spherical coordinate wave equation, we need the solution of the associated Legendre differential equation, which is when m is not equal to 0. So here's some Legendre polynomials of the first kind, p, and the second kind, q. And here's how cosine of theta relates to x, right? Here's the range of x, here's the range of theta. These functions form an orthonormal expansion basis in the polar angle theta, which is really, really cool. Once you get a hang of these, you get a handle on them, you'll be able to do a lot in this coordinate system. You feel very empowered.
How do Legendre polynomials differ in sort of size to normal polynomials?
To normal polynomials? Normal polynomials are not orthogonal, right? If you have 1, and then you have a0 plus a1x plus a2x squared plus a3x cubed, so a normal power series, those are not orthogonal polynomials. If I integrated x into x squared dx from -1 to 1, or where I'm trying to apply this expansion over, I would not get 0, right? So these are polynomials that are orthogonal, and you can think of them as being constructed using what's called the Gram-Schmidt orthogonalization from a power series. So they're orthogonal polynomials.
So there's less, it's a smaller infinity of Legendre polynomials compared to normal.
No, so there's still infinite terms, right? But the thing is, these polynomials these are orthogonal. If I take this function, any one of these, and multiply it by the other, and I integrate from -1 to 1, I get 0. So they're all orthogonal, which really helps when you do expansions of functions in terms of them. You can find the coefficients very easily. All right? Yes. The next?
No, that's it.
Previous.
So what? Okay, we have a G here, we divide.
G is our solution. Right?
Two terms for minus values and plus values.
Yes. It was exactly like we did in cylindrical coordinates. We have our solution, which is a Legendre polynomial here. It's linearly independent with the negative argument as long as p is not an integer. So we can stop there. If p is an integer, we have to construct a new solution using this same approach we did in cylindrical coordinates. When p is an integer, and we obtain a third solution, which we call Legendre function of the second kind. And now our solution in general contains an expansion to these two linearly independent functions.
Yeah, but why don't we do that? Divide it into functions for minus and plus.
Oh, you mean here?
Yes.
Yeah, we do that because the solution that we got here, right? Here has an even series and an odd series, which we can solve. So we know that if p is not an integer, this is being quoted or stated to you. If p is not an integer, then you can have a separate solution, another solution, which is the minus, which is linearly independent from this. So basically, just stated it here. You can construct two linearly independent solutions, one having a positive argument, one having a negative argument, if p is not an integer. Okay, question?
I might have missed the point. What exactly is m here and that is meaningless?
M, okay, we've set m equal to 0 first. So the differential equation that came out of our, let me see if I do it like this. The differential equation that came out of the wave equation has m in it, right? This one has an m. So there's some other separation constant that we haven't considered yet. We will. This is the one we have to solve in the end. We're just solving the Legendre ordinary differential equation with m equal to 0 as a warm-up.
Okay, so we are not taking that part into consideration.
Not yet, right? Where did that m come from? It came from the azimuthal order. So whenever we set this azimuthal dependence to the separation constant, we chose m. So what we're finding is that the theta variation is linked to the phi variation, right? That means that I cannot choose these separation constants or eigenvalues independently. Once I choose n, then m is defined. Once I choose m, n is defined. I have to choose them in a particular combination, right? So the azimuthal order is not independent from the polar angle, the order of that.
Okay. Then we also assume the x to be 0 in ordinary differential equation. So why exactly?
Choose x.
X as 0, right below that step where we assumed m to be 0.
Yeah, so we're just doing that to solve, the ordinary differential equation first, right? Okay, so yeah, the next thing we did, to understand it, right? We have to understand what Legendre polynomials are first. Here, right? So we solved the Legendre differential equation first. So we're gonna solve this one, but just to understand what these functions might look like, it's easier to solve this one first, and then we'll complexify it and solve the m not equal to 0 case. All right? Okay. So we're here, yeah? All right. So we solved the ordinary Legendre differential equation, but that's not the one we want to use for our spherical coordinate expansion. We want to solve the associated Legendre differential equation when m is not equal to 0. So when m is not equal to 0, the differential equation is called the associated Legendre differential equation, and we've rewritten it here, right? This is the one we need to solve. The solutions to the associated Legendre ODE can be obtained from the solution of the Legendre ODE, that's why we solved it, from the following, all right? So y of x is the solution to this differential equation. This should be g. I don't know why I put y of x, right? This is a differential equation in terms of g. This should be g of x is equal to a1 times p and m. Remember I told you we're going to introduce the superscript m plus b1q and m of x, all right? These are called the associated Legendre functions the first kind, the associated Legendre functions the second kind, right? And the relationship between the ordinary Legendre polynomials and the associated Legendre polynomials are on this slide here. That's why we solved the Legendre differential equation first, because we can construct the solution to the associated Legendre differential equation by using these formulas here, all right? Derivation of these is not trivial, so I did not include that, and I'm not asking you to do that. But if you want to solve this differential equation, you need to be able to obtain these solutions first, and we did that, right? P and Q.
Does it have like a similar property to Bessel functions? Differentiate Bessel function in one order, it kind of.
It does have a relationship. It's not the same one though, right? But yeah, there's a differentiation relation. All properties of all these functions in the back of your book for the course. All right, any questions? So here are some of the associated Legendre polynomials. Now there are two scripts to worry about, the subscript and the superscript. So these all have a superscript of 0, right? So first we're showing you what the superscript zeros look like with the subscript varying. We get these polynomials, all right? These are for P0, 3. So m is 0, but n varies from 0, 1, 2, 3. We get these polynomials. They are related to the ordinary Legendre polynomials, right? When m is equal to 0, we expect that these solutions should be the same as the Legendre differential equation, because the Legendre differential equation is the associated Legendre differential equation with n equals 0. So these solutions are the ordinary Legendre polynomials. Now here, when m is equal to 2 and n varies from 0 to 3, we get these solutions. We can construct these from the ordinary p's using the formulas on the previous slide. Here, when n equals to 1, or m equal to 1 rather, and m equal to 3. So you have 0, 1, 2, and 3 for m, and 0, 1, 2, 3 for n. You have all these polynomials. There are more. You can get these on Wikipedia, or you can construct them using that formula on the previous slide, or in the back of your book. It's probably the best place to find them. And here are the Q's, right? These are orthogonal polynomials in theta. Very nice. What do they look like? Here's some plots of these shows associated Legendre polynomials. Still the domain is -1 to 1, or pi to 0, right? Theta. And if you plot these, the first one, p0, 0, p0, 0, the blue line is a constant, it's equal to 1, right? So you need a DC level whenever you expand any function in terms of some other smaller functions or series of them, right? The DC level is the place you expand about, so shift the DC level, that's this one, right? Of course, there's another coefficient in front when you do the actual expansion. These are just the bases, right? So it could be A1 times P0 or A0 times P0 in your expansion, which means A0 will give you the DC level. P10 is P1s. These all have zeros, so these are the same as the ordinary Legendre polynomials, right? Here we have P1s. So now you see they get a little more crazy, but these are still orthogonal. And you have P1, P31, P21, P11, P01. They're all plotted there. And then we have P32, P22, P12, P02 are here. All right. Okay, good. Very nice.
Inverted form, the second insert picture just seems flipped, except it's scaled.
Slightly different, right? Look at the magenta curve.
The shape is negative.
Yeah, they have. It looks similar to. It looks inverted, reflected about the x, right? Okay. Now we need to solve the radial differential equation, right? We solved the polar one. Here's the radial one. This was related to the Bessel differential equation. Now I've repeated it here. So if you multiply through, if you open up this derivative using the product rule, and you multiply through by f, then you get the differential equation at the top of the slide. And the solutions to the ODE of this one are related to those of the Bessel ODE that we saw for cylindrical coordinates already, which we call Jn, right? Remember when we did that lecture, I told you that we're going to solve integer order Bessel functions for cylindrical coordinates. And when we got to spherical coordinates, we do half integer orders, right? I don't know if you remember, I said that last lecture. Here it is, n plus 1/2. They're half integer order. If you evaluate the Bessel functions at half integer order, and their argument is beta r now, and you multiply by this coefficient, which has 1 over the root r, root of pi over 2 beta r, then you get the spherical Bessel functions of the first kind, the solutions to the spherical differential equation of the radial variable. They're small j here. So the cylindrical ones, the ordinary Bessel functions have capital J. The spherical Bessel functions are traditionally denoted with a lowercase j. All right? So remember that the cylindrical coordinate Bessel functions, what kind of decay did they have? I don't know if you remember. They have a decay with respect to rho, right? 1 over what? Almost, right? In cylindrical coordinates, it had a square root outside, right? 1 over the square root of rho. Oh, sorry, 1 divided by the square root of rho, yeah. So it's 1 over root rho, right? So the circumference of a circle grows with respect to the radius as proportional to the radius, right? The circumference of a circle is 2 pi r. So the circumference grows with respect to r, proportional to r. And the power then has to decay with respect to r. The power is the product of the two fields, E and H. So individual fields, E and H, have to decay with respect to, or decay proportional to 1 over the square root of rho. Because when I multiply them, I get 1 over rho. And that makes the power conserved independent of the circle's radius that I integrate the power density over to get the power. Right? I saw that at last lecture, right? Okay, so now, so this already has a 1 over square root of rho in it. Now I multiply by another 1 over the square root of, let's say, r. This is 1 over the square root of r. Now these field components decay as 1 over r, because 1 over the square root of r times 1 over the square root of r becomes 1 over r. And we expect in spherical coordinates that our field decays 1 over r, because the surface area of a sphere grows proportional to r squared. So the field, the power has to decay proportional to r squared. Sorry, yeah, r squared. So each of the fields had to be 1 over r. That's the purpose of this coefficient. This makes this decay as 1 over r, which we need for fields in spherical coordinates. Anyway, so once you have the solutions in spherical coordinates, cylindrical coordinates, you can obtain those in spherical coordinates by evaluating these Bessel functions as half integer orders and multiplying by these coefficients. And the same holds for the spherical Hankel function of the first kind. the spherical Hankel function, the second kind, which are outward waves. These are inward spherical waves, and the spherical Bessel function of the second kind. Yeah? Good, we solved everything. Very nice. So you don't have to think this hard when you solve these problems in scattering and wave guiding problems in these coordinate systems. You just have to know that these functions are the expansion set. And then once you know where they come from, then you just evaluate these in some software package and add them up, which you'll do later in the course. All right. But you need to know where they come from. So in spherical coordinates, we have traveling waves and standing waves. The traveling waves are the spherical Hankels, and the standing wave are the spherical Bessel functions. We can construct solutions F1 and F2 as either standing wave set or a traveling wave set. We can have standing waves only in theta, right? Because nothing leaves the coordinate system in theta direction. It's bound. Same with the azimuth. Everything leaves in the r direction, right? So we'd have standing waves here for P, and you can have either P and P or P and Q, depending on whether n is an integer or not, right? And then we have the azimuthal functions, either j and phi or cosine and sine. Good, all right. So in the end, all you need is this, right? This is, after all of that, you just need this. When you solve for E of R, right? Or A of R or F of R or whatever. Actually, A of R and F of R are the only ways we can solve this, right? So A and R and F of R are constructed from combinations of these functions. And then once you piece that string together, you apply the boundary conditions. I think we'll do that next. Then you get some solution in terms of these functions. If you want to plot it or evaluate it, you just have to go into your software package and evaluate the Legendre polynomials and because it's going to be a summation of these, right? It's not going to just be one P and M. It's going to be, summation of P and M from 0 to infinity or minus infinity plus infinity. And you're only going to need so many terms until the series converges. You're going to sum over n and m, all right? We'll do that later in the course. But we're going to need all this. So here are the spherical harmonics. I tried to plot these for you so you could see them. They're called spherical harmonics. They're on the surface of a sphere. So let's say this is a unit sphere. And I multiply the polar and the azimuthal expansions here. And we have m and n as our variables, right? So let's see how they're linked. Once I choose an m for the azimuthal order dependence, then that fixes part of my polar dependence. So here's m varying in this way, n varying in this way, and I plotted what these look like. So mn equal to 0, then I get just a constant on the surface of the sphere. So I have some function which is defined on the surface of a sphere. R is fixed. So the surface of the sphere has some function. I want to express that function in terms of a weighted superposition of simpler functions, right? Expansion functions or harmonics or some kind of series expansion, right? Orthogonal functions. These are the orthogonal functions that I'm expanding. So an arbitrary function that I can draw on the surface of the sphere just like this can be expressed as part of this, A0 of this plus A1 of that plus A2 plus A3. So it has some of this in it, some of that in it. And these are orthogonal and they span the whole set, or they span the space, so you can expand any function in terms of them. This is what they look like though, all right? Think of them as like on a 1D line, you have polynomials that you can expand some function in terms of. Here you're expanding some function on the surface of the sphere. Yeah.
Like when we have like a planetary sun and we have oscillations in the planet, but like and it distorts kind of without gravity or something.
Okay.
How is that when we're oscillating in a spherical space, is it still a sphere or is it distorted?
Okay. Either R is going to change, right? Or you might be able to represent that with these harmonics. These are very popular harmonics. They're very well known spherical harmonics. Maybe you can solve,
It's just R that's changing. What is there?
well, you can either make R change or maybe you can represent it in terms of these polynomial or these functions. You might be able to do that. Yeah. Okay, good question. All right. So let's do an example before the course ends so you piece everything together. Let's write the solution for SAR or psi, r, theta, and phi components of the fields within a spherical cavity. So here we have some spherical cavity. There are fields inside of this thing, a source inside, and it's a PEC sphere. Nothing can get out, but it'll start reflecting like a mirror. light inside a mirror and it will set up a resonance, a mode inside of there. And you can either put another probe in there to extract the energy due to this resonant cavity, right? At some frequency, that's gonna be, it's gonna increase resonantly, right? Every small input you put from a source is going to add up in phase to a larger and larger and larger input, that's resonance. Or if I'm at the wrong frequency, every time I put in an extra little bit of energy, it's out of phase with what's already in the cavity and it kills it, right? So that's off resonance. So some source in here, radius A, my solution psi, r, theta, and phi, I can represent as F times G times H. And we know that F is either in terms of standing waves because we're bounded in R, so they're not angle functions, they're Bessel, with A1, Jm beta R, B1, Ym beta R. Then we have standing waves are bounded in theta. So our expansion for our solution in theta was PNM cosine theta plus QNN cosine theta, and they're periodic waves in phi, which is C3 cosine plus D3 sine, yeah? All right. Applying the boundary condition will allow us to determine the wave numbers and most of the coefficients. For example, the fields must be finite at r equal to 0. We already know that y-ends are infinite at the origin, right? Because they're related, they're constructed from the y and capital Y-n from the cylindrical coordinate system. And we know that one went to minus infinity at 0. Therefore, B1 must be 0, right? And they have to be finite at theta equals 0 and pi. It's B1 is 0 because of finiteness at the origin, and D2 is also infinite at theta equals 0 and pi, so we have to get rid of those. All right, since all ym is singular at r equals 0, and the QNN is singular at theta equals pi and 0. So if we reduce it to now this, AMN equals to Jm beta r, so the spherical Bessel in R, some Legendre polynomials in theta, and we have these two orders in azimuth. If the problem we're scattering instead of a cavity, meaning we have a plane wave source outside of the PEC sphere, a plane wave comes in and scatters off the sphere, we'll solve that problem later in this course, then we would have traveling waves on the outside, right? Because they're not bounded anymore. And then we'd have the same orders in the azimuth and polar angles, right?
So, and with the particle in the box type thing, DFT waves, what is this, if you have like a spherical thing, you drop the particle, would the DFT solutions be spherical?
What is DFT?
Dynamic functional sphere.
Okay, let's come back to that. Let's talk in my office, yeah? Okay. Okay, so the solution, okay, the differential equation we saw was del squared plus beta squared psi equal to 0, right? I don't know if you caught that, but our differential equation we derived for A and F was del squared plus beta squared psi over R, right? Okay, so it's probably poor notation because what we solved was del squared, we solved this, right? When we solve this differential equation, we solved this one. Del squared plus beta squared psi equal to 0. But really we wanted psi over R. So in order to relate these two things, we just need one piece of information here. This is the last slide in this series. So in spherical coordinates. Remember the wave equation derived from Maxwell's equation in terms of psi over R, which is this one for TE and this one for TM. So to get to that solution, if psi of F, G, and H is a solution to this one, which we already constructed, then R times psi is a solution to this, right? Because psi equal to A over R, AR is equal to R psi. So it's just a change of notation, a change of variable. Okay, so there are new radial functions now, because this only affects the radial functions, because it's R is the only variable involved. The new radial functions are denoted Bn hat. There's a little hat. These are the functions that you're going to use in solving spherical coordinate problems, scattering, right? So the Bn hats, everything that Bn stands for either J, Y, H, or Hn. Now, okay, so it goes back to capital letters in spherical coordinates. These are the actual functions you have to use, right? Because the differential equation we derived as psi over R. So these are the expansion set that you use, but they have a hat, denoting that they're for spherical coordinates, and of course they're in terms of R, not rho. They're related to the spherical Bessel functions we derived on the last slide, but we multiply by R because of this whole thing over here. All right? So we get beta R times this is this. So here we are, right? All right. So thus, F1, only the R expansion is modified, is really A1J in hat plus B1Y in hat. And F2 is HN hat and HN hat 2. All right, and they're just related to the solutions that we derived on the last slide, the spherical ones are multiplied by R, and we know that the spherical ones are related to the cylindrical ones without the hat through this expansion, hat integer order and that. Now we add the beta R. All right, a lot to take in. All right, good, but we're done with that. The next one we're going to do in generalized coordinates. So you did spherical, rectangular, cylindrical. Now you can do any, or not any one that you can separate the wave equation in. We're going to do it in generalized coordinates. Then you'll feel really powerful. That's it for spherical coordinates. All right, thank you guys. I'll see you. Don't forget your homework's out now. He's doing a week, and I'll see you guys next Tuesday. All right. All right, have a good one.